Climate change and extreme weather events like we've seen this year in Germany or at the moment in Canada are one of the biggest problems facing humanity right now. The research of the next two scientists can help us to understand more about weather, about climate, and about the huge amount of data we can collect. The next presentation is on climate and Earth system data, collecting data with weather balloons and understanding them with AI. Please welcome Dr. Scarlet Stadtler. She's principal investigator of the project KISSDE, which stands for AI Strategy for Earth System Data. And she's postdoc at the Institute of Advanced Simulation, Jülich Supercomputing Center. And welcome as well Dr. Johannes Laube. He's a group leader with the European Research Council Starting Grant, and he's working at the Institute of Energy and Climate Research. Scarlet and Johannes, last week the UN Climate Conference was concluded in Glasgow, and climate change was given a lot of media attention. We all heard about it, but issues like climate and air pollution too are part of your everyday life, of your work life at least. How does this affect your personal life, I was wondering? So does it have any influence maybe on your personal contribution to reduce air pollution or to fight climate change, Johannes?
Yes, so we do have regular family discussions on how to, for instance, reduce our CO2 footprint.
And do you have an example where you already
Well, we do try to fly less or not at all if possible. That's
a good start, I would say. What about you, Scarlett?
I only eat vegan food to avoid the industrial farming and the deforestation associated with it.
Vegan food, yeah, that is a big impact as well, I think. So now we're looking forward to the presentation, Scarlet Stadtler and Johannes Laube.
What motivates us to understand the Earth and climate systems? Well, we want to be certain about our future and the future of our children. Also, for climate mitigation, we have to know what will happen, where it will happen. But also on a personal level, understanding our Earth and climate system helps us taking decisions. For example, if I want to build a house, it would be very beneficial to know what climatic conditions will be there. Will it be hot and sunny, or will it be wet and cold? This will then lead to me deciding how to build the house. But another reason is climate protection. In the 1980s, we understood that chemical CFCs harm our life-protecting ozone layer in the stratosphere. So banning the production of these chemicals helped all of us. But how can we gain this valuable understanding of our Earth and climate systems?
There are three fundamental ways to advance our understanding of the Earth and climate systems. So 1, we can conduct simplified experiments in the laboratory. 2, we can observe parts of these complex systems directly. And 3, we can simulate these systems in a theoretical way by building climate and Earth system models. One example for an experiment in the lab I want to mention is our work on new greenhouse gases. CO2 and water vapor are well-known greenhouse gases. However, there are dozens of other greenhouse gases present in the atmosphere, most of them man-made. Their number is ever increasing, so we are always on the lookout for new ones. We need to be able to estimate the effect of greenhouse gases on global warming, which is why we run experiments. The way greenhouse gases work is that they trap infrared radiation, so that's heat, and therefore prevent it from leaving our atmosphere. So we took a sample of one of our new gases and exposed it to different types of heat radiation, and it looked like this. The gas trapped some of the heat radiation quite well. Those are the spikes. And after some calculations, we arrived at a number, 3,300. This gas is 3,300 times more efficient than CO2 in trapping heat radiation. Its concentration in the atmosphere is increasing, but luckily is still tiny. We still need to keep an eye on this one, as it has the potential to become a serious threat. and a double threat too, as it is a CFC, so it also destroys the ozone high up in the stratosphere. As you already know, one of the things that interests me most is the state of this ozone layer in the stratosphere. To understand what is happening, we have to get to the stratosphere, and this is a bit tricky, as the stratosphere extends from about 10 kilometers above us to about 50 kilometers. Passenger aircraft can usually get to about 13 kilometers, and special research aircraft make it to about 20 kilometers. So the best way of getting higher up is to use balloons. In the past, scientists have used large research balloons that can lift gondolas of several hundred kilograms and contain huge amounts of helium. This is, however, very expensive, and it's also very dangerous to land such a gondola in any populated region. Imagine a massive metal construction with strange-looking humming and flashing devices descending into your back garden. Luckily, instruments to obtain precise measurements of atmospheric parameters have become smaller and smaller. This is why we now have a sensor package that weighs just about 4 kilograms, and we send it to the stratosphere from our institute backyard with a much smaller balloon, essentially a weather balloon. A biggish weather balloon, but still a weather balloon much smaller and much cheaper too. It looks like this. Or, if you're lucky, can look like this. In the first picture, you can see one of our main sensors, which is called an air core. It essentially is a long piece of tubing that is open on one end, so it empties on the way up as pressure decreases with increasing altitude, and then it fills on the way back down, therefore collecting air from around 30 kilometers to the ground. And here's one example of how the data looks like. What you see is the concentration of one important CFC and how it changes over time near the ground in blue, and all other colors are results from between 10 and 35 kilometers. The lower the concentration, the deeper we got into the stratosphere. What you also see is that the passenger aircraft in black doesn't really get there. However, the research aircraft in red and the weather balloons in orange do. And since we started launching those weather balloons in 2016, we are gathering a lot more data from the stratosphere, and with a lot less effort and money. My final point is that, of course, you cannot get the same amount of information from the small weather balloons that as you can get from research aircraft and large balloon flights. So it is also very important to carry out these other flights and fly more and heavier scientific instruments. Luckily, we did one of these rare, large, and somewhat dangerous balloon flights in northern Sweden this summer, and I did bring along a video from the launch to show you. Perhaps you spotted the blue light flashing, which is our instrument from Jülich. The flight went very well, and we now have some exciting results to work on.
As Johannes said, There's a third way to gain a deeper understanding of our Earth and climate systems. It's by building models and running them on a computer. Numerical modeling has a half-century-old tradition. It started with very simple algorithms. And thanks to observations and experiments, we increased our understanding of the systems and included more and more interactions and processes into these models. Nowadays, we have highly complex numerical models based on mathematical formulas. But still, the world is not fully understood. A novel approach to improve our understanding of Earth and climate system is by using artificial intelligence. Artificial intelligence, in short AI, can explore empirical relationships between various forms of observational data and the Earth system. By empirical relationship, I mean that we do not have a mathematical equation. For example, we can train our AI to predict the air quality based on environmental characteristics. So there is not a known chemical relationship for the relationship between land use, population density, altitude, and the air quality. But intuitively, we as humans, we know that if we are in a highly populated area, highly industrialized, we might have a poor air quality. AI has no intuition, but in contrast to us humans, AI is able to find this unknown formula connecting the environmental characteristics and air pollution. So, with help of AI, we can combine data describing the environment with air quality observations around the globe. But how does this actually work? So we teach our artificial intelligence by giving it thousands of examples. With example, I mean we have a pair of data describing the environment and the corresponding air pollution observation. Imagine it like this. The station is located, or we are surrounded by a high population and mountains. We are in the sunny south, and we have a corresponding air quality observation. This is only one example. We have thousands of examples around the world, and we present these examples hundreds of times to our AI. So, finally, our AI figures out the empirical relationship between the environmental characteristics and the air quality. So an AI which already learned the relationship is a model. We can input environmental characteristics to this model and get an air quality estimate. And this approach is quite different from what I've told you before with the numerical modeling. For numerical air quality modeling, you need to know atmospheric chemistry and physics. You have to define the chemical model while writing down the chemical equations. And this chemical model then takes in atmospheric variables and gives us a prediction. But in contrast, AI figures out that for us. So now that we have this model by our AI, what can we actually do with it? So first, we can feed in data from areas where we do not have any air quality observations. Here you can see how our AI predicts the air quality in regions without any observations. This air quality estimate in itself is already very valuable for the people who live there, for their agriculture, and also for their decision-making. But as I said, we want to base our decisions on our AI predictions. Therefore, we have to make sure our AI is reliable and that we trust it. As you can see on this map, we only colored areas where we are certain that our AI is doing a good prediction, or we can explain that prediction. So explaining AI is actually a pretty new research field. It's all about figuring out how the AI does its predictions. Concretely, how does our AI connect the environmental characteristics to the air quality? And the answer is, it depends on the type of AI. So for the sake of time, I will only talk about one AI called random forest. The random forest consists of decision trees. Each decision tree predicts the air quality given the environmental characteristics. Each prediction is slightly different. And finally, we hand in all the predictions of the single decision trees average, and this is the prediction of the random forest. So studying the trained random forest gives us actually insights into how the AI works, how it does its predictions. Here you can see a visualization of explaining a specific air quality prediction with our trained random forest. It also helps us to further analyze our air quality observations from an AI perspective. Using AI to explore Earth and climate data is a very promising modeling approach to gain a deeper understanding in our Earth and climate systems. So, in summary, at Forschungszentrum Jülich, we use different ways to improve our understanding of the Earth and climate. Of course, there are many more interesting examples we couldn't show today. We continue developing new and exciting experiments, observations, and new modeling approaches to predict current and future changes to these complex systems. Thank you.